Good morning, everyone. Thank you very much for coming to class. I hope you guys are having a good start to your Thursday. I hope that if you're going to go out and have a fun time this weekend, that you pick a really clever costume and you're safe and um yeah, do those responsible things and eat lots of candy. Could anyone add to the chat what their favorite candy is? I will add to the chat my favorite candy. Good. Good. Snickers, yeah. Blue Sour Patch Kids, nice. Nice. Um, my kids will be trick or treating. My oldest son is going to be the main character, Charlie Conway from the Mighty Ducks. He was going to be Grimace, the McDonald's character, but uh, switched out of that last second. My let's see, my 7-year-old is going to be a let's see, vampire, I think. He's not. I can't remember what he is. My 5-year-old is going to be a he's going to be a vampire, and then my 8-month-old is going to be I don't know. Um, he might one year we just put the youngest kid, or we've done this a couple of times where we just get our youngest kid and put him in pajamas and then put dots on the pajamas and say he's a puppy. We'll see. That might be what emerges this year. At any rate, I plan on taking a considerable portion of their candy after they go to sleep. But, you know, they'll stay up and eat lots of candy. And since it's on a Friday, so then that means I'll have to stay up extra late to eat all their candy. Okay, so what we are talking about today is we are talking about intermolecular forces. Now, this is a term that sometimes you'll hear me refer to. Um, sorry, you'll hear me say IMF, and that is in reference to intermolecular forces. Um, Last time, what we were talking about, or in our previous lecture, we were discussing uh, PowerPoint is opening, and we were discussing solutions. Now, I want you to be thinking about intermolecular forces, and I want you to be thinking about a solution. Because if you think about, let's say, a glass of water, here's my glass of water, and it's filled up to about here. Um, do you think there's one molecule, a single molecule of H2O? Add a Y in the chat if you think that there is a single molecule of water in there and only a single molecule. Add an N if you disagree that it's more than that. Okay, cool. So when we, look at this glass of water at like the molecular level, this is going to be my oxygen and this is going to be my pair of hydrogens. The red balls are going to represent my hydrogens, and then the clear one represents the water. So we've got this kind of, we have lots of these molecules, and we need to be thoughtful of or we need to think about, well, how does this molecule right here interact with this molecule right here? Now, this depiction right here of these two water molecules, um, is there a bond, or have I drawn a bond to connect these two molecules? I haven't. But it's kind of like if you're riding the subway or something like that, or if you go to a big city and you're riding the subway in New York City or something like that, um, maybe you go with your family and maybe you're like, okay, well, we are a family unit. We've got to have some sort of forces that keep us together. And usually that force is like your phones, because it's like, okay, we've got to be able to communicate. Um, but if you get into the subway and you're standing next to someone that you don't know, do you have to, or you're going to be like aware of them and you're going to say, okay, well, I'm not going to stand this close to that person because I don't really know them. that would be called an intermolecular or interpersonal exchange, interpersonal interaction. Now, what we need to do is make sure that we know the difference between an intramolecular force and an intermolecular force. We have talked about, though we have not used this term intramolecular. Now, I want you to think about that as being distinct and different from an intermolecular force. So when we talk about like a bond, a covalent bond or a polar bond, I'm going to say or a covalent bond or a polar bond or an ionic bond. Those are all great examples of intramolecular forces. So whenever we talk about like electronegativity, for instance, well, that is the sharing of electrons, and electronegativity gives us a sense of which of the atoms that are sharing these electrons wants them more. But nevertheless, we're talking about sharing electrons between, well, two atoms that are a part of one molecule. So another way to say this is intramolecular would be within one molecule. Give me a number in the chat if that makes sense. Just focusing on intramolecular, not necessarily comparing yet. Okay, so we've got some depictions of this. So I'm going to go ahead and I'm going to switch to green. Green is going to be the way that I indicate my intramolecular interactions. This intramolecular, 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 intra. Done, done, and done. Okay. Now, intermolecular. Whenever I think of intermolecular, what always comes to my mind is I always think of the interstate highway system. So this is, well, connecting. I'm going to say connecting slash within. Well, I'm going to say within. Maybe I'll also go to say amongst, just because I like saying that word, amongst more than one molecule. So we see those typically depicted with like a dashed line like this. So now I've circled our intermolecular forces. Now, one of the challenging things about this is that both of these contribute to like properties of something. Um, but when it comes to the physical state, our physical state being is something a solid, liquid, or a gas, what ultimately determines what state something is? And the answer to that is intermolecular forces determine that. So more times than not, when it comes to like, if you look at a glass of water and you ask the question, well, has anyone ever, give me a W in the chat if you've ever heard of the term surface tension. Okay. Now, if you've ever heard of surface tension, maybe you've heard of surface tension with respect to water. Could anyone tell me, just kind of generally, does water have a high surface tension or a low surface tension? High. Yeah, water is kind of, I don't know if I would say notorious, but water is a substance that's considered to have a high surface tension. Oh, sorry about that. So water with a high surface tension, it has less to do with and this would be our H2O molecule. Water's high surface tension has less to do with this bond and more to do with this intermolecular force. So this contributes to physical, I'll say physical state. I almost added an E, physical. Physical state. I'm going to say state, and I'm going to put a slash, property. And so if we think about water as having a high surface tension, that's because the individual molecules within a water solution are held together pretty tightly. So that means that the intermolecular forces are strong. Okay, now I'm going to skip this next slide and instead go straight onto the different types of intermolecular forces. There's three major types of intermolecular forces, and I'm going to focus and really emphasize one more than the others. And that is the strongest of our intermolecular forces, and that is hydrogen bonding. So I'm starting on the far right here. Hydrogen bonding is what basically makes something have a, or actually, let me rephrase that. Hydrogen bonding is a strong I'm going to say interforce. Now, with hydrogen bonding being a strong intermolecular force, I'm going to jump back here and sorry. Great. Um, if I'm going to switch colors, now what I want you to pay attention to is what I'm writing in black. Okay. So this right here is a hydrogen. I'm going to erase the red. Done. Erase a little bit of this so it's a little bit less noisy. Um, the red balls are oxygen, H, O, H, H. Okay, so this right here that I'm circling in black is a intermolecular force, and specifically, it is a hydrogen bond. Does anyone want to add the symbol for the element that is one of the necessary elements for hydrogen bonding? The letter symbol. Perfect. I love it. Hydrogen. Great. Hydrogen bonding requires hydrogen. So I'm going to go ahead and add this detail down here. ReQ, H. It also requires something else. Now, with that said, I'm going to look at this little description. Hydrogen bonding, only polar molecules. So only a molecule that is polar is going to have any sort of hydrogen bonding or participate in hydrogen bonding. So only polar molecules with OH, NH, or FH. When you hear F or fluorine, what term comes to mind? And I'll give you a little bit of a hint. I'll give you two hints. Fluorine is the most dot dot dot, and the term that I'm specifically thinking about starts with an E. And it might perfect. Electronegativity. So what I'm getting at is, well, oxygen, nitrogen, and fluorine. If you visualize those on the periodic table, they're all right next to each other. It goes NOF. So these three electronegative elements negative, not nega 5, negative elements are required. So too is hydrogen. But remember, is this between one molecule or is it amongst two or more molecules? Add one for it's within one molecule or two for two. Perfect. So if I just did this, if I said, hey, OH, and I asked the question, is there hydrogen bonding in this right here? Well, this whole thing that I've circled, that's just one molecule, or that's part of one molecule. So if I ask the question, does this show H bonding. What's your answer, Y or N? Remember, this is only one part of a molecule. We need two or more. So this alone, no, it doesn't. Does everyone follow me there? If I rephrase this and and then also another kind of clue is whenever you see this solid line as opposed to dashed line, I want you to think, oh, okay, this solid line, just like back here, it represents an intramolecular force. And hydrogen bonding is an example of an intermolecular force. So this right here, no, it does not display or demonstrate an intermolecular force or hydrogen bonding specifically. Now, if I were to do this, I'm going to the upper left-hand corner. I'm going to draw a molecule of NH3. Now, NH3 has, well, it has a lone pair of electrons on nitrogen, and that is one thing that's going to make this molecule polar. And whenever I look at my definition for hydrogen bonding, well, it only occurs between polar molecules with OH, NH, or FH. Do I have one of those things? I do. I'm going to go ahead and circle this in red. I'm going to say, okay, well, here is part of one molecule that might lead to hydrogen bonding. Can you give me a Y or N if you follow so far that this is only part of the question or this is only part of the model? Okay, great. Now, what I'm going to do is I'm going to say, all right, well, I've got this dashed line. I'll make this solid line a little longer. I've got this dashed line going from hydrogen, and what I am going to look for to say whether or not there's hydrogen bonding is I want to see a dashed line going from a hydrogen to an oxygen, a nitrogen, or a fluorine. So let's say it goes to this. Okay, and then I've got this right here. Does this display hydrogen bonding? Yes, it does. Okay. Now, is there anyone who did not follow that? If I had to guess, because I'm thinking back to myself whenever I first learned about hydrogen bonding, is there anyone who didn't follow this completely? The answer is yes. I struggled with hydrogen bonding like crazy. Now, I want to go ahead and erase this, and I'm going to put together basically like a checklist for if there is hydrogen bonding. And the first thing that I want to put on there is I'm going to say, rather than jumping straight to, is there hydrogen? I'm going to say, are there two or more molecules? If the answer to that question is no, and sorry, is there H bonding? That's the big question that we're asking. Does everyone follow that? Give me a Y or N in the chat if you follow that. Okay. So, is there hydrogen bonding? Yes or no? I don't know. In order to answer that question, I've got to go through this sort of schematic or this flow chart. My first question is, are there two or more molecules? If the answer to that is yes, then I'm going to proceed to my next question. My next question is, well, do I have OH? Let me erase that. OH, NH, or FH in both molecules? And if the answer to that is yes, I've got good news. We are done. We can say and we can confirm and affirm that yes, indeed, there is hydrogen bonding. So if our second question says yes, then we can say, yes, there is hydrogen bonding. Could you, everyone say Y or N if they follow that? Okay. Now, what I want to do is I'm going to give us an example. And we're going to work through an example problem to kind of visualize that. Okay, so first things first, I'm going to draw one molecule, water. Great. Um, does this alone show if we have hydrogen bonding? It does not, because our first question is, are there two or more molecules displayed? If the answer is no, there are not two molecules, well, then we can't say whether or not hydrogen bonding is taking place. Now, the next thing that I'm going to do is I'm going to draw CH4. Ooh, will these two molecules have hydrogen bonding taking place between them? Hmm. Ooh, no, no. You are absolutely correct. Because let's think about our questions. First, I'm going to go shorthand on this first question. Two molecules? Yep, we're good. Second question, follow up. And this is the definitive one. OH, NH, or FH, or HF, whatever, in both? In this case, in this example, no. So, no H bonding. Could everyone give me a 9 in the chat if they follow that? Okay, great. Now I'm going to go do one more. Okay, CH4. And then CH4. Is there hydrogen bonding between these two molecules, Y or N? No, there's not. Because I don't have OH, NH, or FH in either one of them. You know what's great, and I'm sure that a handful of y'all, if not everyone, recognize this, but as soon as I wrote CH4, you were kind of done. Because is this molecule capable of ever hydrogen bonding? Nope. It doesn't have OH, NH, or FH. So it doesn't matter what the other molecule is. Now, last one. Can hydrogen bonding take place between these molecules? Yes. And it loves to. And that's why water has a couple of very interesting and important properties. One, it's a high boiling point. I'm just going to say high BP, not blood pressure, high boiling point. Second, it has a high surface tension. That's why, if you ever like do a belly flop off a diving board, it's going to hurt like heck because water has such intense surface tension. And why does that have that intense surface tension? Well, it's because you get these hydrogen bonds between water molecules that they make this really complex network where they all just love to be right next to each other, and it almost makes like a solid or a crystal-like structure. Okay, so our strongest intermolecular force is hydrogen bonding. Why does it cause high boiling point? That's a great question. So the high boiling point is because think about it like Okay. When you visualize a solid at, let's say, actually, here, let me just, this is going to be a rough model of a solid at almost like the molecular level. All of the different molecules that make up this solid, they're very organized. They're very close together. They're happy together. They don't need to really move around. And when you have something like water, all of the individual water molecules, they will do that same thing even in a liquid form. And that's not what everything does. So if we had CH4, for instance, oh, didn't. CH4 as a liquid, it would look a little bit more like this. Here's one molecule, here's another, here's another, here's another, here's another. And they're just kind of bouncing off each other because they're not like, hey, we're friends, we should stick together. Whereas, because the forces that hold these together, I'm drawing the arrows to represent those, they are not very strong. Whereas liquid water, LiQH2O, well, liquid water, the forces that hold them together are super strong or are stronger, I'll say. So it's almost, I hope this, sorry, does any of that make sense? And you can be honest. Okay. Okay. So so now let's go back because now we're going to talk about the weaker forces, which are going to give a better explanation than these arrows that I drew. It takes more heat friction to make them move. Yes. Yes. Because they're already like, if you're liquid water, the molecules are like close together and they're like, hey, we like staying together. You got to give us a good reason to get away from each other. Whereas with CH4, they're like, I don't really care. The forces that hold us together are just kind of like, nah, we're not really invested in anything. Okay. Um, so now let's go on. We're going to talk about the weakest. I'm going to jump over here. The weakest intermolecular forces. These are known as dispersion forces. If you've ever taken a chemistry class, I'm going to erase this. If you've ever taken a chemistry class, you maybe heard of these referred to in a couple of different ways. Dispersion forces are sometimes known as induced dipoles. They are induced. They are sometimes referred to as LDF or London dispersion forces. And I think the best way or what's helpful for me to think about dispersion forces is I always think about CH4. When I draw CH4, I've got the, and I mean no disrespect to this, but I've got a pretty boring molecule. And whenever I say that, I mean it's boring because, well, it's nonpolar. It's kind of like a game of tug of war that's just going on and will go on for forever. Because it's nonpolar, it is, and this is one of the reasons, but it's symmetrical. So, and if you've ever, and okay, this is a molecule that's a hydrocarbon. It's carbon and hydrogen. That's all there is to it. There's lots of compounds that are hydrocarbons, and they show these same sorts of things. Now, can everyone give me a slash to get on board? Or here's my model. This is a CH4 molecule, and here's another CH4 molecule. Can you give me a slash if, okay, I'm on board that these, what right now look like eyeballs, are representatives, or actually, I'm going to draw them a little larger, representations of an entire CH4 molecule. Can you give me a slash in the chat if, okay, cool, I'll follow you. I'll go along with you. Okay, great. Now, when we look at, let's say this bond right here, I've drawn an arrow between carbon and hydrogen in this bond. Do you think that in a shared pair of electrons, do you think that electrons move? Or do you think that as soon as they're shared between two atoms, they just like lock in and they never move? Give me an A if you think that there's movement to them, and a B if you think they never move. Kelly, you're absolutely right. Electrons are in motion. Now, with that said, the way that I think is helpful to think about electron movement is let's think about, ooh, I've got it. I've got what I think is a great example. Um, can you give me a one in the chat if you've ever been on a canoe? Okay, great. Now, if, let's say, here's our canoe, here's a person, here's a person. I want you to think about this canoe as being kind of like, well, here's one atom and here's another atom. So the two electrons are the two people in the canoe. The only difference is that is, you know, the people in the canoe generally don't move around. So that's where it doesn't work out. But what would happen if both of the people in the canoe went to one end and they ended up like oop, here and here? You'd have an uneven weight distribution, right? So you'd have like, oh man, lots of weight is going in one direction. Now, what is the charge of an electron? Just give me the symbol in the chat. Great, negatives. So if in our bond, and I'm going to come back to the models of the circular models of the CH4 molecule in just a moment, but would you agree with me that if we had our two electrons over here, this side would be more negative? Give me a Y or an N if you agree that side would be more negative. Okay, great. Now the opposite of that. Well, the opposite of negative would be positive. And so if this side is more negative because of the placement of those electrons, then this side right here, where I'm drawing a Y, that's going to be relatively more positive. Would you agree with that? Give me a Y or an N to the chat. Okay, perfect. So CH4 is a great example of a molecule that is nonpolar, that more times than not, you have electrons, yeah, they're moving around and stuff, but sometimes what can happen in a CH4 molecule, and this happens very briefly, but we have all of the electrons kind of concentrate onto this side. And let's say that we have two molecules of CH4 and that happens. We've got this other molecule, I'm going to label molecule A of CH4 and molecule B of CH4. All of the electrons migrate to one side, the left side. Is everyone with me there? Give me a 7 in the chat if you are. Okay. Now, what that means is that if this side is more negative, then the other side of the molecule is a little bit more positive. Okay, so if this side, where I'm now writing positives, is more positive, then what happens to molecule B? Will molecule B and the left-handed negative side of that molecule, will that be attracted to the right side of molecule A? Yes. Does everyone follow me there? Give me a 6 in the chat if you follow. Okay. Now, an important thing about that is that that movement is very brief. This happens, and then it kind of it sorry, it occurs and then it undoes itself. So we have this attraction between these two molecules, but it's almost as soon as that attraction takes place, well, then they kind of relax and they go back. So that's why we could think about this as kind of a instantaneous, instantaneous, or brief interaction and attraction. Does everyone follow me there? Give me a Y in the chat if you do. Okay. Okay, so we have these two molecules that are close, but it's very brief. And because it's very brief, it's not nearly as strong as your hydrogen bonds. Your hydrogen bonds, by comparison, well, those are super strong. By comparison, I mean, if you have OH, NH, and FH in two molecules, you're going to have hydrogen bonding. If you don't have OH, NH, or FH, you're not going to have that. You're instead going to have, well, these positive and negative poles that sort of appear briefly and then they kind of disappear. Now, those are our bookends, our molecular forces, our intermolecular forces. Our dispersion forces are super weak. Those are where you have a pole, a dipole, a positive or negative end appear and then disappear. Your hydrogen bonds, that's where you have an electronegative element like oxygen, nitrogen, or fluorine bound to a hydrogen, and then a nearby hydrogen attracted to that. Okay, now our third range, and I've been drawing all over this. Could everyone give me on a scale of 1 to 10, 1 being I'm great, 10 being, oh, I'm lost. How do you feel about hydrogen bonding? Justice is on top of that. Great. Okay. Okay. Now, dispersion forces. The way that always felt about dispersion forces was like, I understand it kind of generally, but what would really be helpful for me would be almost like a checklist. I like that. A 7.5 or 5. Um, a checklist was really helpful for me whenever it comes to really kind of classifying these. So what I'm going to do is I'm going to go ahead and build on this right here, the list that we developed for is there hydrogen bonding. We can take this and basically say, what type of intermolecular force is there? Now, with that in mind, if your answer to question number 1 here, are there 2 or more molecules? If your answer is no, is there any sort of intermolecular force? No. If there's only one molecule, you can't have 2 molecules interacting. It's kind of like if there were no individual states in the United States, would we have an interstate highway system? No, we wouldn't. The interstate highway system connects Texas to Louisiana, connects Louisiana to Arkansas. Okay, if there was only one state, we would have no interstate highway system because there's no inter. Okay, so if our answer to this question is no, then, well, we don't care. Now, what we can do is we can take this second question and say, okay, well, that's one proving ground to answer if there's hydrogen bonding. If we have those in both molecules and they're, yes, we've got hydrogen bonding. If your answer is no to this, then the question is, okay, well, are any of my molecules polar? And if the answer to that is yes, then we've got what's known as a dipole-dipole interaction. Okay, I'm going to go on to right here. And what we'll do is we'll look at a dipole-dipole interaction. So let's go back. It's a dipole dipole. So put an emoji in the chat if you think that we've got two dipoles. Okay, good. In the event that you're like, yeah, I'm on board with there being two dipoles, but what's a dipole? Dipole is just another term which it's one of those words, the more that I say it, the sillier it sounds. I just said it and I was like, am I about to talk about diapers? I almost am. But a dipole is a polar molecule. So, polar molecule, polar molecule. So, if you have two polar molecules, you'll have a dipole-dipole interaction. Now, if you think back to our CH4 molecule, well, CH4 is non-polar, but we have these dipoles or these positive and negative poles that appear, but then they disappear. A polar molecule is going to have this slightly positive end and slightly negative end, but it's going to be there kind of indefinitely. Does that make sense? Give me a wire end to the chat. Okay. Now, if you're thinking, okay, well, what's a polar molecule? Let's see. I'm going to try to come up with, let's go with just a second. I gotta pull up the periodic table in another window. And if you're thinking, this guy doesn't have the periodic table memorized, you're right, I don't. Okay, let's go with no. Anytime I try to come up with something like this, I end up coming up with something that's not polar, so that's a problem. Or sorry, that yeah, is not polar. Let's go with la, 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 la. Perfect. I've got one HCN. And that is the Lewis structure for this molecule. Um, then let's go with let's go with B. No. Um, I don't want to go with an ion or with a polyatomic ion. Um, let's go with um I also yeah, you know what? No, I'm not going to go with that. I'm sorry for dragging my feet on this, everyone. I just want to get a good option. No, that's not. Okay, I'll go with SO2. Okay, so I'm going with HCN and SO2. So I'm going to give you the Lewis structures of these. SO2 looks like this. Oh, it's the eraser function. Switch to pen. Done. SO2 looks like this. And I've got lone pairs of electrons on each oxygen. Okay, now let's look at these molecules. If we look at HCN, for example, um, we have, or do we have symmetry? Nope. If I were to slice this down the middle, on the left-hand side, I've got a hydrogen. On the right-hand side, I've got a nitrogen. So this is not symmetrical. Would everyone agree with that? Give me a wire end to the chat. Sorry, I'm also asking for the Y in the end just to bring everyone back because I took way too long figuring out the molecules that I wanted to draw. Okay, so this is not symmetrical. And since it's not symmetrical, is it polar P or is it N nonpolar? P polar, perfect. So it fits that. Okay, now SO2. Ooh, this is kind of tricky. If I split it down the middle, that looks a little bit symmetrical. But, ooh, you know what? That lone pair of electrons on that sulfur, does that, give me a Y or an N, does that impact the polarity of our molecule and designate it as polar or nonpolar? Yes, it does. Does it make our molecule P polar or N nonpolar? Okay, great. So we've got two molecules that are polar. Now, the way that I always kind of treat this is where I see the kind of concentration of my lone pairs of electrons or my electrons, I'm going to go ahead and consider that to be a kind of partially negative area. So when I look at SO2 and I look at HCN, and actually, you know what? What I'm going to say is I've got this region right here and this lone pair of electrons makes my two molecules polar. So if I go back to my checklist, first question, two or more molecules. Answer is yes. So now I can go on to my next question. My next question is, do I have an OH, NH, or FH in either or both of my molecules? I'm going to say in both. In this case, no. So since I said no to this, do I know anything about this type of bonding or type of interaction between these two molecules? Yeah, it tells me not H bonding. Great. Thank you, Kelly. Does everyone follow my flow chart so far? Specifically at that second question, could you give me a Y or an N if you follow what I did and what I concluded so far? Okay. So I can conclude no hydrogen bonding takes place between these. And there might be somebody who's looking and they're like, but there's a hydrogen. You're right. But hydrogen alone does not tell me that there's hydrogen bonding. I need an OH, NH, or an FH in both of them. And I do not have that in either of them. Okay, so now, in addition to saying there's not hydrogen bonding, I'm going to go on to item number three. And item number three is, well, are both molecules polar? Well, yeah, they are. So since both molecules are polar, I can say, well, this is a dipole dipole interaction. And what I can say about that is that that is stronger than the dispersion forces. Can everyone give me a 6 in the chat if you follow this sequence of questions and the conclusions that we drew? The last conclusion that I drew was really kind of referencing back to this table right here. Dispersion forces are the weakest. Dipole-dipole are kind of your mid-range. And then hydrogen bonding are your strongest intermolecular forces. Okay. So with that, one of the things that we can say is that, well, actually, let's go ahead and I'm going to open up this poll question, but we're going to kind of work through this together because there's a little bit of additional information that I want you guys to know. So what we have here is three different molecules. I'm going to open the poll question, save to meeting poll, save as meeting poll, done. And we are going to look at the types, or we're going to look at the molecules. If you want to answer the poll question, go for it. If you want to wait until it's correct, that's fine as well. So what we have is three different compounds: methane, ethane, and propane. These are all hydrocarbons. Now, methane, ethane, and propane, these are organic compounds. You're probably familiar with propane because, well, you can get it to, make some burgers. Methane, give me a Y or an N if you're familiar with methane, and you can share whatever context you're familiar with it in. Well, I'll be honest. Whenever I hear methane, I always think of cows, um, not just dairy cows, but cattle in general, and I, farting. Sorry, I had to say it. I mean, maybe I didn't, but I elected to say it. Um, so methane is a gas. Propane is a gas. Give me a Y or an N in the chat if you think that ethane is also a gas. These are all carbons and hydrogens. The black ball represents a carbon, the white ones represent hydrogens. Now, what's the difference between these three molecules? Well, methane has a formula of CH4. Ethane has a formula of C2H6. Propane has a formula of C3H8. Now, a fair question is, well, what types of interactions exist between these? And if we go through our checklist, one, if imagining we've got two or more molecules, what forces hold methane or a mixture of methane together? Two or more. Well, I could give you this sort of question and ask this, like what holds methane together? Well, for our first question, are there two or more? The answer is yes. It's kind of implied in that question. The second question is, do we have OH, NH, or FH? In any of these, the answer is no. Okay, so there's no hydrogen bonding. Third question, are any polar? No. And I'm going to go back this slide right here. When we were constructing our example of dispersion forces, well, we used methane as our example. So since they are not polar molecules, we have no other conclusion than to say none are polar. So the forces that hold them together are dispersion forces. Okay. Now the follow-up to that is, well, what's the question? The question says which substance has the highest boiling point? And as soon as you've identified that, as you've identified the types of interactions, then you can say, well, the highest boiling point is associated with the largest molecule. Which one of these is the largest? Well, the one with three carbons and eight hydrogens. So propane is the substance of these three that has the highest boiling point. I'm going to leave that open for just a minute because I got to go to get another question coming, but um, I'll give you another 10 seconds or so. Sure. So I got a private message question of why. Propane is going to have the highest boiling point because it has the highest molecular weight. It has the most atoms. They're all made up of carbon hydrogen, but propane has the most carbons and hydrogens. Sound good? Okay, so now I'm going to wrap up, or I'm going to conclude poll question, And now we're going to go on to our next poll question, which let's go through this same sequence. If you had a mixture of Cl2, Br2, and I2, first question, do we have two or more molecules? Yes, we do. Second question, do we have, I'm going to say 2 plus. Second question, OH, NH, FH. Do we have any of those? Nope. So is there hydrogen bonding? Nope. Third question, are any of these polar? Give me a Y or an N if any of these are polar. I mean, we could look at if Cl2, for example, if you were to draw out Cl2, it looks a little bit like this. F or I2 looks like this. Br2 effectively looks the exact same. Are any of these compounds polar? No, they're perfectly symmetrical. So if they're not polar, then you don't have dipole-dipole. So last but not least, we are looking for, well, since they're not polar, then we can only conclude that it's dispersion forces. So then this question reads, well, which one of them has the lowest boiling point? You could look at it in the same way that we looked at the last question. The one with the highest boiling point was propane because it was the biggest. So then the opposite of that question, you could rephrase this and make it easier for yourself. I'm going to say that H2, or sorry, I2 is going to have the highest boiling point. Therefore, Cl2 has the lowest BP because we've got the lowest molecular weight. Cl2 is going to weigh about 70 because I did 35 plus 35. Br2 is going to be about 160. Iodine, or I2, is going to be about no, I can't add. I forgot how to add. 127 plus 127 is 254. I tried answering the polls, but I think it's not working since I'm on my phone. If you're on your phone, you can still participate in the polls. You just have to hit more, and then it will bring up the polls option. It's the three dots usually indicate more. And tap that. Okay. I'll give you another few seconds. I'll leave that up because now we're going on to our next question, or not our next question, but our next kind of model. Molecule polarity is important because if you see polar molecules, then you're going to say, okay, well, it's dipole-dipole interactions that hold these together. Now, I'm going to go on to this question right here, but we're going to work on this one together. This will be our third and final, I believe, our final question. This has A, B, C, and D. Say, okay, so which one of these substances has the highest boiling point? Okay, well, let's talk about this for a second. What we want to do is really sorry, if it still doesn't work, I don't see a poll option. Can I email you the answers later? No, I'm sorry. We've been using polls for a long time, and so I need you to sort that out on your phone. So what we're doing is we're looking at question number 1, 2 plus molecules. Yeah, we've got 2 or more molecules. Number 2, and for all of these, we have 2 or more molecules. Our next question is, do we have an OH, NH, and FH? And if the answer to that is yes, then we're going to have a hydrogen bonding. Okay, now I'm going to stop the last poll. I'm going to open up this one. So let's look at each one of these individually. For H2, we've got two or more molecules. Is there H bonding here? Ooh, this is really tempting because there's hydrogens. Ooh, yeah, yeah. No, there's no hydrogen bonding. Okay. So actually, you know what I'm going to do? I'm going to make a little table. Oh, great idea. H bonding. Then we've got dipole dipole, which I will just list as DD. And then last but not least is dispersion, DISP. So let's just go hydrogen bonding for all of them. Straighten that line out. H2, Joel, come on. Here we go. Here we go. Yep. Go. That's better. Does H2 have hydrogen bonding? No. So I'm going to put an X there. Actually, I want to make this as clear as possible. So um, I'm going to put an X if that type of interaction is present. For HCl, ooh, does that have an OH, NH, or FH? Does not. So we're looking at a big no. So I'll put no, no. Methane, do we have hydrogen bonding? No, we don't. Methanol, is methanol capable of hydrogen bonding? Yeah, because do we have an OH? We do. So I'm going to put a check mark there. Now let's just go through the others. Just dipole, dipole. Well, H2 is a completely nonpolar, it's a symmetrical molecule, so no. HCl, hmm, is that a polar molecule? Give me a Y or an N in the chat if this is a polar molecule. Absolutely. So would we have dipole-dipole interactions? I'm going to put a check for that. Yes, we would. Methane. Is this a polar molecule? No. And then last but not least, methanol. And this is one of the places where it's kind of tricky. Um, do we have like, if you think about the letter of the law, is this a polar molecule? Yes, it is. So is it capable of dipole-dipole interactions? Yes, it is. Now, what I want you to do is I want you to think about this as, yeah, it's capable of dipole-dipole interactions, but it's also capable of hydrogen bonding. Just because it's using one type of interaction does not mean that the others are off the are like no longer options. So, will methanol right now arguably is like, well, it's got multiple types of interactions. Dispersion forces. Does H2 have dispersion forces? Yes, it does. So I'm going to put a check there. HCl, does it have dispersion forces? Yes, it does. Methane, does it have dispersion forces? Yes, it does. Methanol, does it have dispersion forces? Yes, it does. So the way I want you to think about this, or what I think is a really good way to think about this, is that if something has hydrogen bonding or is capable of hydrogen bonding, it's also going to do dipole-dipole. It's also going to do dispersion forces. It's dynamic. It's capable of all these different types of interactions. Could you give me a Y or an N in the chat if that makes sense? Now, could you give me a 6 in the chat if this table was helpful? Okay. So if you do that, then it helps to kind of systematically go through each molecule. Now, there are some folks who say, oh, yeah, you got to start with dispersion forces because everything has dispersion forces. But for me personally, I like to start with the strongest forces because as soon as I have those strongest forces, then I'm much more capable of answering my question. As soon as I filled in this first column, I was done. And you can do that same thing when you're taking your test or doing any of your homework or anything like that. Okay, so ultimately, and this isn't going to take too much longer, I'm going to close the poll in just a second. Yeah. We were talking about solvents and solutes. We were talking about preparing solutions. All of this has to do with how things interact. Um, if you took something like CH4 and H2O, let's say CH4 and H2O versus, let's go with N. No, what did I do? What was my? Go back and use one of my molecules earlier that I took. Oh yeah, there we go. HCN and H2O. Thinking about how these two substances interact and these two substances interact. Give me a letter, A or B. And if you're not ready to, take your time. But if you think B, the molecules in B will interact better, put B. If you think the molecules in A will interact better, put A. Now, thinking about the types of interactions that two molecules of water like to interact with. Water loves hydrogen bonding. It's super good at it. So water can do H bonding. It can do dipole-dipole, and it can do dispersion. Would everyone agree with that statement? Give me a Y or an N to the chat. Okay. Now, water over here, same thing, H bond, dipole-dipole, and dispersion. Okay. Now let's talk about CH4. CH4, it's not going to do hydrogen bonding. It's not a polar molecule, so it's not going to do dipole-dipole. So CH4 really is left to dispersion forces. Some pretty weak interactions. HCN. It can't do hydrogen bonding, but it can do dipole-dipole, and it can do dispersion forces. We've got these two compounds right here, which can do dipole-dipole and dispersion forces. Check, 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 check. We've got these two compounds, which can basically only meet at dispersion forces. If you think about this, like thinking about these two things making a solution, the more things they have in common, the more things that they are like one another, the better they're going to react and interact with one another. So now let's go back to that A versus B. Do you think the substances in A are going to interact better, or the substances in B are going to interact better with one another? Awesome. B is correct because we've got those two substances, dispersion forces and dipole-dipole, that they're very like one another. And what I'm getting at there is CH4, if you added methane or if you added and thinking about like another hydrocarbon, like gasoline is a hydrocarbon. If you got gasoline and poured it in water, it's not going to mix well. It's not going to make a very good solution. Could you give me a Y or an N if you follow that? Okay. Now, along those same lines, we have different types of solutions. A carbonated beverage is an example of a solution. The solvent is water, and the solute is a different phase. It's gas. A sugary drink. Well, the solute is a solid, whereas the solvent is water. A glass of wine. Well, the solute is a liquid, and the solvent is basically water. This goes back to like dissolves like. Whenever you're thinking about will this dissolve well? Think about the types of intermolecular interactions that can take place between those two substances. The more things that are in common with one another, the better off they're going to be. Now, will something dissolve? Well, a polar solute will dissolve in a polar solvent. A nonpolar solute will dissolve in a nonpolar solvent. A ionic solute will dissolve in a polar solvent, and a a polar solute will not dissolve in a nonpolar solvent. So the more complements that you see, the better off these substances are going to be at basically dissolving with one another. Now, I believe this is our last poll question for the day. Which substance does not dissolve in water? And try to think about these as, okay, water loves hydrogen bonding. If something else in this mixture can hydrogen bond, and let's just go H bond. Can ammonia hydrogen bond? Yes. Can methanol hydrogen bond? Yes, it has the OH, as water does as well. Can hexane hydrogen bond? No. Can nitrate hydrogen bond? Well, it can't hydrogen bond, but now let's go on to our dipole-dipole. And you know what I'm going to do is I'm going to complete the table, but I'm going to go ahead and check off ammonia, methanol for dispersion and dipole-dipole. If you're confused about that, well, I know that if something can hydrogen bond, it can also dipole-dipole, and it can also have dispersion forces. So by it having hydrogen bonding capabilities, it has everything else also. So is everyone good with that? Give me a 6 in the chat if you're good with that. Okay. So what I'm going to do as a result of that is I'm going to eliminate A and B because those will dissolve in water because they've got that hydrogen bonding. So now I'm down to hexane and sodium nitrate. Okay. Well, one thing that I want you to know is that, and this would be on the table of polyatomic ions that I give you on your exam, this is a polyatomic ion. This is an ionic compound. If something is an ionic compound, it is capable, it has positive and negative parts of it. So it is capable of dipole-dipole interactions. It's also capable, therefore, of dispersion forces. So sodium nitrate, by it being an ionic compound, I'm going to eliminate that. And that leaves me hexane. Is hexane capable of dipole-dipole interactions? No, it's not. That is a hydrocarbon. That is boring. It is a nonpolar compound, so I'm going to say no. All that hexane is capable of doing is dispersion forces. And because I was able to eliminate A, B, and D because of these sort of stronger interactions, well, I'm left with C. Hexane is not going to dissolve well in water. All right. So C is the correct answer. We're at 71% of the class got that. Now, with that, the last thing that I'll mention is that sodium chloride is an example of an ionic compound. If you add sodium chloride into a solution of water, it's going to dissolve because it's an ionic compound. It can do these dipole-dipole interactions. Now I'm going to go ahead and stop my recording. I'm going to stop my share,